Yeah, so happy birthday to Samson, whom I got to know over the last couple of years. Since I moved to the US, I see him very often, and yeah, I learned a great deal of physics, some of which people already mentioned, but in particular, this talk is about anomalies, a subject in which he played an important role in developing the first few results, so which I'll mention soon. So I'm looking forward to many more years of overlap and discussions. So happy birthday. So this presentation is mostly based on some upcoming work, but also I'll mention some previous work that I've been involved in with mostly Davide Gaiotto, Anton Kapustin, Nari Seiberg, Jaume Gomis, students like Vladimir Bashmakov, Adar Sharon, and now also with Kentaro Mori, who is a postdoc at the Simon Center, and students, Konstantin Rompedakis and Saif Nashri. But most of the presentation is based on presumably the work that's now in preparation, but I'll also review a lot of the recent developments by many other people, and I will not even mention probably 10% of the people that I should mention in connection with this huge subject. So the beginning of this subject is on Notter's theorem. So there is a very abstract and modern way to think about Notter's theorem, which is that if you have a symmetry, whether it's continuous or discrete, doesn't matter. What it gives you is a topological surface. So this way of presenting Notter's theorem is, of course, a generalization of what Noether originally envisioned. What Noether originally said was that if there is a continuous symmetry, then there is a conserved current. But then, if there is a discrete symmetry, then there is no statement. But there is a way to say Noether's theorem in this fashion, which works equally well for discrete and continuous symmetries, since if you have a conserved current and you integrate it over some space-like slices, say, then the operator that you get is a surface operator. It's a codimension 1 operator, which is independent of the shape of the slice. So a way to think about Noether's theorem, which applies equally to discrete and continuous symmetries, is that the theory is equipped with some topological codimension 1 operators. So they don't depend on the shape of the surface, of the codimension 1 surface, but there might be an interesting algebra of such topological surfaces. And so one is led to develop some kind of mathematical framework for the algebra of codimension 1 surfaces. And this led to a huge outpouring of results in the recent 5-10 years of generalizations of the notion of symmetry. We learned a great new deal of things about the algebra of such objects and so on. So this is going to be the central thing in the talk. I'll present some of these new developments, and also many applications to gauge theories, to gauge theory dynamics. So if there are any questions, please stop me.
Actually, there is. What's the statement about this surface? Like, such that what?
Well, if in Noether's original story, then she said that there is a conserved current, right? And then you could integrate it over a d-minus 1-dimensional space. You integrate star j in some differential form notation. And this gives you some operator, which, if let's suppose we exponentiated it with some coefficient alpha, this would be a unitary. But this unitary is independent of the surface. So this unitary is labeled by the surface, but it's independent of the surface. If you take some closed surface and you deform it slightly, the unitary is the same. Let's say it acts in the same way on the Hilbert space, so to speak. However, this does not mean that this surface is completely trivial, because if there is a local operator here, and you compare the same surface with the local operator outside, it's not the same thing. So there is an algebra when codimension d objects cross this codimension 1 object. So this leads to some algebraic structure. That's the notion of acting with a symmetry on the local operator. Okay, so that's what I'm going to explain now. So if you acting with a symmetry on the local operator, which is what we usually do when we have symmetries, corresponds in this abstract language to just encircling the operator, which is codimension D, by this codimension 1 surface. And that's the same as acting on the operator in the usual adjoint representation. And then there is a non-trivial algebraic structure which doesn't have to be commutative. You can encircle this bunch of operators first with sigma g, and then with sigma g prime, and that can be fused. They can be fused to sigma of gg prime. That leads to in the normal situation, when you have symmetries, this leads to a group structure. It's associative, but it's not commutative. So that's how we think about the symmetries, that there's some fusion of such topological surfaces. Now, of course, once you start drawing these pictures, you are led to think about more complicated objects. Here I've been just thinking about some codimension 1 surfaces that might have some interesting fusion rules, but you're also led to think about more complicated objects, such as the junctions and intersections. What happens when two such surfaces intersect? What happens when there is a T-junction? Or by a T-junction, I mean something like this. What happens if there is something like that? So you're led to more complicated questions which are not answered by Noether's theorem. So as I already said, in the case of continuous symmetries, these surfaces are obtained from exponentiating the integral of the current. And if you look at textbooks about symmetries, nobody talks about these things in this way. People just talk about correlation functions of currents. And that's how people found anomalies in the 80s and 70s and even the late 60s and so on. They looked at correlation functions of currents. And clearly, correlation functions of currents capture a lot of the data about these topological surfaces, since the correlation functions of topological surfaces can be obtained from all the correlation functions of currents. If you knew all of those guys, you would know a lot of stuff about these topological surfaces. But that's only available for continuous symmetries, as I said. So an important phenomenon that's associated to symmetries is the notion of 't Hooft anomalies. And one should not confuse the 't Hooft anomalies with ABJ anomalies. ABJ anomalies are essentially the statement that there are no topological surfaces. So historically, ABJ found that something that seemed like a symmetry is not a symmetry. So that means that there are no topological surfaces. But 't Hooft anomalies are much more delicate. 't Hooft anomalies concerned with situations when the symmetry actually exists. The theory is equipped with a bunch of topological surfaces. And the 't Hooft anomaly is a statement about the algebra of these topological surfaces. So the simplest case is a Z2 symmetry. That's a case that I'm going to discuss now, just to explain how an anomaly is manifested in the algebra of such surfaces. But in the continuous case, the situation is rather well known from textbooks. People look at correlation functions of currents and ask about the divergence of the current. Let's look at the Z2 case, however, which is much more instructive and much simpler. In the Z2 case, there is one trivial topological surface, which is the unit topological surface. And then there is a non-trivial topological surface, sigma. So sigma might have some non-trivial braiding with local operators, that some operators could carry a Z2 charge. So suppose you have, this is a local picture. So you should imagine something much more complicated. Let's say you have some Riemann surface, or you have an arbitrary space, let's say some Riemann surface, but locally near some region, you have these two topological surfaces that look like this. So this is just a local picture of something much more complicated. So suppose you have a region in some Riemann surface where the two topological surfaces touch like that, and you want to compare, and then you try to split and rejoin them in this fashion. So the outgoing lines should be the same, basically, right? It's just splitting and rejoining. And you ask, what is the relation between these two answers? And the relation could be either a plus or minus sign, as you can prove, because it's a Z2 symmetry. So the case where you get a plus sign from this split rejoin move is the case where there is no anomaly, and the case where there is a minus sign is the case where there is an anomaly.
Can I have a question? Can you imagine a more complicated relation where there is just some linear combination? I don't know. Is this really the most general thing that you can imagine?
No, this is not. This is just a sufficient. This is a sufficient and necessary condition for there to be a Z2 anomaly. This is in 2 dimensions. These are lines. Sorry, this in 2 dimensions. These are just lines. And so they're codimension 1. And this is true in 2 dimensions. This example is in 2 dimensions. In higher dimensions, these are codimension 1 surfaces. And you can imagine many, maybe more complicated things. But nobody has worked out the mathematical theory in higher dimensions yet. We don't know what's the correct mathematical terminology. In 2 dimensions, I'll mention that what is this mathematical object. It has a name in the literature, and we understand it very well. So in the Z2 case, the anomaly is just the statement of this rejoining and splitting. And you can think about it as a discrete gauge transformation, if you like. So as I said, the plus corresponds to the situation that the Z2 symmetry has no anomaly, and the minus corresponds to the situation where there is an anomaly. This was recently also explained in a very nice paper by Lin and Shao. So how do you see that the minus case corresponds to an anomaly? You can ask yourself, could I gauge such a Z2 symmetry? By gauging, gauging means that you sum over all, you make these surfaces transparent. So gauging is the same as assuming that these surfaces, codimension 1 surfaces, become trivial. But of course, if there is a minus sign, you cannot gauge it, because you cannot make the surfaces invisible if there is a minus sign, since it's inconsistent. You cannot make them invisible all at the same time due to this inconsistency. So a minus sign is like the statement that you cannot gauge the symmetry. Or more precisely, gauging is ambiguous. So we see that in 2 dimensions, we have a somewhat nice understanding of what an anomaly means in terms of these topological surfaces. In higher dimensions, there is no well-developed mathematical framework yet. But I'll talk more about it. The next thing that I want to discuss before jumping to applications is the question of what are these anomalies good for. So as we know from the 70s and 80s, the continuous anomalies that appear when there are massless fermions in even space-time dimensions, they're very useful to constrain the spectrum of bound states, massless bound states. So continuous anomalies have something to do with massless particles. They could be Nabu-Goldstone bosons like pions, or they could be massless fermions. In the discrete case, however, the anomalies may also imply a topologically non-trivial vacuum. So that's something new that appears in the discrete world, that some of these discrete anomalies may also be saturated by a topologically non-trivial wave function for the ground state. So the discrete anomalies teach us that either the ground state has massless particles, or there is some topological field theory, essentially. Now, mathematically, in the continuous case, it was realized in the 80s, which is what I mentioned that Samson was involved with, that the classification of these anomalies has to do with the cocycles, group cocycles. This kind of group appears in 2 dimensions. In the discrete case, a very similar result is true. And also, Kapustin and friends have argued that it should really be a cobordism group in the most general setting. So there is a classification, at least in 2 dimensions, of the possible such things. So this story is rather clean. This is the essentially classical Netter theorem plus what it means to have an anomaly. Stated in such a way that it applies for discrete and continuous symmetries alike. And recently, there has been a huge amount of work on generalizing the notion of symmetry. And these generalizations of the notion of symmetry can be done in multiple ways. So there were generalizations in several different directions. I will not speak about all the possible generalizations of the notion of symmetry, but I'll mention 2, which are very important for applications.
Yes, but there always should be some consistency condition which replaces cocycle condition.
Right. So
You cannot have unrestricted situation.
That's right. So you can ask, what is the mathematical framework that incorporates junctions, intersections, the split join move? And the answer is not known in general, but in 2 dimensions, it's known. I'll talk about it soon. It's something to do with fusion categories, modular tensor categories, these kind of words that maybe you are familiar with. But in higher dimensions, nobody yet came up with the correct axioms. But I'll talk about 2 generalizations that appear to be very useful in lots of applications. These are interesting things because this really generalizes the notion of a symmetry. So this point of view is useful because it allows you some interesting generalizations. So I'll speak about 2 generalizations. One is when there are topological operators which are not codimension 1. So they could be codimension P. They have nothing to do with ordinary symmetries, but they still may exist. There could be gauge theories or interesting quantum field theories or even lattice systems where there are topological codimension P codimension P operators. This is called in the literature higher symmetry. Another generalization which is more recent and also a little bit harder to understand is the notion of non-invertible topological operators. What does it mean to be non-invertible? For the usual nutter kind of codimension 1 surface, codimension 1 topological operators, for every group element G, there is an inverse group element G minus 1. And if you fuse them together, you get a trivial thing. So for every surface sigma, there is another surface sigma prime, so that together they fuse to nothing. But this doesn't have to be true. There could be gauge theories or interesting lattice systems or quantum field theories where there are some topological operators that have no inverse. So these are non-invertible topological operators. So, and these things could be mixed up. So there could be interesting systems where there are both higher symmetries, non-invertible symmetries, and it would lead to a complicated algebra of topological objects. And as I said, the mathematical framework in general is not known, but we have many partial results. Now, these generalizations are very useful because on the one hand they're new and they allow some new results to be derived, but many concepts that you're familiar with can be generalized to this framework. So you can talk about anomalies. So there is a notion of anomalies even for this more general setting. And the notion of anomalies is essentially about splitting and joining such surfaces. And then you could talk about the notion of gauging. You could talk about the notion of symmetry breaking. So inflow, even a formalism of anomaly inflow and descent equations that Samson and Fadeev worked out can be generalized to some extent. We already know some of the basic results in this field. So while this generalized notion of symmetry is new, some things from the past can be borrowed, and they continue to make sense. So one piece of terminology that's useful to know. Yes? Oh. Okay. So what I'll do in this talk is that I'll first present applications of the first generalization, and then I'll present applications of the second generalization. And I'll show you that this leads to useful results about Yang-Mills theory in 3, 4, and 2 dimensions. 4, 3, and 2 dimensions. So first we'll start from the first, codimension P topological operators. So I will assume that all the codimension P topological operators are invertible. I'm not going to mix up these two generalizations, though they mix up in some applications. I will not mix them up. I'll study some systems which have invertible codimension 2 operators, and then separately the other case. So first I'll talk about codimension 2 topological operators, which are called one-form symmetry, and this terminology was introduced in this paper. So they call this codimension 2 surfaces one-form symmetries. It's just a name. One can prove that such objects must be abelian, because they are codimension 2, you can take them through each other. So the fusion must be abelian. So one-form symmetries are always abelian, unlike ordinary nutter symmetries, which may be non-abelian. So that's a small lemma. It must be abelian. So what do these things act on? Since they're codimension 2, they cannot act on local operators. They cannot act on codimension D objects. They must act on codimension D-1 objects. And codimension D-1 objects are just lines. So while the codimension 1 operators that Netter had acted on local operators, these things act on lines. So there is a non-trivial algebra with lines. So the same picture holds. You encompass a line inside a codimension 2 surface, you shrink the surface, and you get a new line, which is acted upon by some abelian symmetry. So now it must be abelian by the previous lemma. What are some examples? So it turns out that any gauge theory in any number of dimensions that has a center that doesn't act on the matter fields has such codimension 2 topological operators. So even SUN Yang-Mills theory has such topological surfaces. I cannot write a Lagrangian for these topological surfaces, but I can manipulate them formally and ask various questions about them. In general, there could be such surfaces that don't have anything to do with the center of the gauge group. We have many examples of that, but I'll not talk about such examples today. We can also try to gauge these topological codimension 2 surfaces. Gauging means that we put some background field and we may even sum over it later. Now this would be a discrete 2-form gauge field, or a continuous 2-form U1 gauge field. So like gauge fields are replaced by 2-form gauge fields. You can also replace the Higgs mechanism by Higgs mechanism for 2-form gauge fields and so on. So the simplest example where there are such objects is just pure Yang-Mills theory in 4 dimensions. So as you know, pure Yang-Mills theory in 4 dimensions has a theta angle, which is valued between 0 and 2 pi, because the instanton number is quantized. This is on spin. By the way, just for simplicity, I'm only discussing spin manifolds here. 4 spin manifolds, 4-dimensional spin manifolds. Otherwise, there are various things that I have to fix in the slides if I were not to discuss just spin manifolds. And this theory turns out to have such codimension 2 topological surfaces, because there is a center that doesn't act on any matter fields. And so it's isomorphic to Zn. So this theory has a Zn worth of such topological surfaces, and one can ask what they're good for. As you know, there is a Clay prize, like $1 million or something, for proving that at theta equals 0, this theory is gapped and confined and trivial. It turns out that these new topological surfaces lead to a very interesting statement about not theta equals to 0, but theta equals pi. So it turns out that you can prove using these topological surfaces that at theta equals pi, the ground state cannot be trivial. And this can be proven rigorously. So there are at the moment 3 possible. So once you've proven that the ground state cannot be trivial, there are essentially 3 options. So one option is that there is maybe some symmetry breaking at theta equals pi, or maybe there are some massless gauge fields. Massless particles. I meant to say massless particles. They could also be gauge fields, but so one of these things has to be true at theta equals pi. So the Clay conjecture cannot be true at the Clay price cannot apply, theta equals pi. It's the opposite.
So trivial means not one-dimensional. It has to be there.
So mathematically, I'm not saying the precise statement because I'm trying to keep it accessible. But there is a notion of anomaly for these codimension 2 surfaces. There is a generalization of the notion of anomaly, and you can prove that at theta equals pi there is such an anomaly. So that means that the ground state cannot be trivial. There must be either massless particles or maybe some symmetry breaking, Nambu-Goldstone bosons, or domain walls or something. Now, we don't know which of them is true, but it's very likely that it's the first that is true. From large N arguments and from ADS-CFT, it seems that one should really favor the first one. So what we expect is that while theta equals pi is confined, trivial, and gapped, and then there's the confinement at high temperatures when you go to the quark-gluon to the gluon plasma phase. At theta equals pi, actually, it turns out that the phase diagram cannot be that simple. There must be something going on already at 0 temperature. It cannot be confined and trivial. And even when you heat it up, this order in the ground state cannot disappear. So one is led to the following phase diagram that we propose following this thing. So this is theta, and this is temperature. T is temperature. So let's focus for a second on theta equals 0. This is trivial. So this is the deconfinement first order transition line. So this is confined, trivial, gapped. This is the standard picture for Yang-Mills theory at theta equals 0. As you heat it up, you encounter this phase transition, and beyond this line, you're in the deconfined phase. So that's the standard picture for SUN gauge theory at 0 theta. However, at theta equals pi, one is led to believe that there is some symmetry breaking. So one believes that here there are 2 ground states, and time reversal symmetry is spontaneously broken. There is some first order line, and then this first order line must in fact cross the deconfinement line because of these anomalies. And this leads to some funny inequality. One can prove an inequality that the time reversal symmetry is going to be restored only after the deconfinement transition. So it's impossible to restore time reversal symmetry before the deconfinement transition takes place. So it's funny that these discrete anomalies lead to an inequality for a phase diagram of just pure Yang-Mills theory. It's a rigorous inequality that you can derive just from these anomalies for higher symmetries. Another very amusing fact that can be presumably one day tested on the computer is that since there is some symmetry breaking here, there are two vacua. So the idea is that at theta equals pi, there are two vacua. This is what symmetry breaking means. And they're related by time reversal symmetry, or alternatively by CP. T and CP are the same, since CPT preserves the vacuum. Since there are two vacua, you can construct a putative universe, where on one side of the universe you're in one vacuum, on the other side you're in the second vacuum, and there is a domain wall that interpolates. That's what in water we call the layer like water vapor layer or something. So this is the discrete analog of a Nambu-Goldstone boson. Nambu-Goldstone bosons are objects that allow you to travel between different vacua, and in the discrete case, domain walls do the same. So actually, from this anomaly, it follows something very strange must be true for this domain wall, which I tried to draw here, but it's probably totally incomprehensible. So let me instead explain it by drawing it again here. What happens is that, let's suppose that you're just in the ordinary, let's suppose you're in one of those vacua. Let's call this vacuum 1, and this is vacuum 2. So vacuum 1 has confined quarks. It has broken time reversal symmetry, but it has confined quarks. So there is a string. If you put two heavy quarks, Q and Q bar, they're going to be confined by a flux tube. But let's suppose now you have this configuration with the domain wall. So there are two vacua, and in both Q and Q bar are connected by a flux tube that's confined. And here is the domain wall. So the domain wall is somewhere here. That's more or less the region where the transition from the two vacua takes place. So it turns out that the quarks are deconfined on the wall. So if you bring a quark near the wall, it loses the flux tube, and it doesn't cost infinite energy to create a quark anymore. So there is deconfinement on the wall, while there is confinement in the bulk at 0 temperature in each of the vacua. The wall itself is deconfined. So if you put a quark and an anti-quark, they don't connect via a flux tube. They might connect by some very weak Coulomb forces, but not by a flux tube. Even more bizarre than that, the quarks acquire fractional spin, so they become anyons. So if you bring a quark to the wall and you circuit around an anti-quark, you pick up an Aharonov-Bohm phase, which is exponent of 2 pi I over 2n. And so the spin of the quarks is fractional. So the quarks are not only deconfined, they also become anyons. And that's a prediction that follows just from these anomalies. So there is a time reversal symmetry breaking at 0 temperature, and on the domain walls the quarks become anyons, and this is their spin. They have a fractional spin. Yeah.
If I artificially introduce an axion now and probe all that dynamically, because then there is a domain wall real.
Yes.
So and if I go through it,
right. So since this thing, there were many papers about what you're saying. In particular, there is I think there is a paper of Sherman and Unsal exactly about this, and maybe also Misha Schiffman. They try to see the implications of this anomaly when you have an actual axion and you have an axion string, or an axion ring, they call it, axion ring. And yeah, basically the same continues to be true. You have some point where there is a concentration of energy, where the quarks are deconfined, and they become anyons. You should really think about this as a quantum Hall state. So suddenly in Yang-Mills theory, there is a wall where there is a quantum Hall state with this gauge, and so this is the topological field theory. Since there are anyons, there is a topological field theory, and this is the topological field theory on the wall. It's SUN-Chern-Simons theory at level 1. That's the prediction.
So in real world, theta cannot be equal pi then?
Right, so this proves that in the real world, theta cannot be equal to pi, because if it were, there would be domain walls that would proliferate and maybe not wiped out by inflation. That would be very sad. So cosmological considerations would rule out theta equals pi in the real world because of this anomaly. However, it may be interesting for other applications in phenomenology that we can talk about later. Okay. Now, in this picture, what I tried was to explain dynamically why the quarks become anyons. So the idea is that these two vacua are related by time reversal symmetry, but time reversal symmetry famously takes dions to monopoles. So here there is dion condensation, and here there is monopole condensation. If you've never heard about this fact that time reversal symmetry takes dions to monopoles, think about Seiberg-Witten theory maybe. That might help. So here there are dions, here there are monopoles, and it's kind of in the wall. You cannot mutually condense dions and monopoles. They're not mutually local, so there is some kind of tension. And the tension is resolved on the wall by deconfining the quarks. So both expectation values go to 0. Both the monopoles and the dions do not condense on the wall. And you get instead a topological phase, which looked like a quantum Hall phase. So that's the, okay, so this is an example of applications in 4 dimensions. Now I'm going to tell you about applications in 3-dimensional Yang-Mills theory. Are there any questions about 4 dimensions? Okay, so the next example is in 3 dimensions. This example still would not involve the non-invertible topological surfaces. It only involves the codimension 2 topological operators, namely a one-form symmetry. So the last example would involve the non-invertible topological surfaces. So another interesting example that recently condensed matter people have encountered, and so we were motivated to think about it, is just Yang-Mills theory. There is no theta angle in 3 dimensions, but you can add fermions. So the simplest thing you can do is to have a gauge theory with adjoint fermions and some mass. That's basically like a joint QCD in 3 dimensions. It's the simplest thing you can do. And this theory, again, has a Zn one-form symmetry because the center does not act on the matter fields. There are these topological codimension 2 operators, which are now just lines. Another fun fact that is not going to be important, except for one little comment soon, is that the m equals 0 theory is accidentally supersymmetric. So it's the minimal amount of supersymmetry in 3 dimensions, which is called n equals 1. There is no holomorphy, so it's not very useful, but it's still supersymmetric. Another technical comment for the experts is that n must be even for this theory to exist. So n is even in SUN. So using supersymmetry, Witten argued around 20 years ago that the Witten index is 0 in this theory. So you take SUN plus an adjoint fermion. It has a very small amount of supersymmetry, just 2 supercharges. And Witten computed the index, and he found that it vanishes. And then everybody believed that the infrared of this theory is just a spontaneously broken supersymmetric phase, namely a single Majorana-Goldstino particle. So just from the fact that the Witten index vanishes, you are led to believe that the SUN gauge theory with an adjoint fermion flows in the deep infrared when you go to very long distances to a single Majorana fermion. And of course, this Majorana fermion is uncharged. It's just the Goldstino. And that's it. So that's what you would think naively, given the information. Say again?
For any mass?
Oh, no, this is just for capital M vanishing. Of course, thank you. Just for vanishing capital M. That's where this argument about the Witten index can be made. That's the only case where it's actually accidentally supersymmetric. Now, when we started thinking about this model using these new ideas about anomalies, we found that this doesn't make any sense for 2 reasons. One, let me start from the second reason because it's easier. This theory, as I said, already has a one-form symmetry, and it's Zn, where n is even. And it turns out that there is an anomaly. So these codimension 1 surfaces, when they loop around each other, there is some problem with splitting and joining, very much analogous to what I explained in the beginning. And there is some anomaly. This anomaly is measured mod n, and it's n over 2 mod n, turns out. For even n, this formula makes sense. And it turns out that this single Majorana fermion cannot match this anomaly. So this contradicts anomaly matching, this idea. This contradicts anomaly matching. So this is not consistent with anomaly matching, because this single Majorana fermion cannot match that one-form symmetry anomaly. Another thing that also leads to a contradiction is time reversal symmetry. The massless theory has time reversal symmetry, and it turns out that this splitting joining issue with codimension 1 topological surfaces, which are the time reversal topological surfaces, leads to a difficulty mod 16. So there is instead of, remember in the Z2 case, it was a plus minus thing. So in the Z2 case, it was a plus-minus thing. It turns out that if you do time reversal symmetry instead, it's a root of 16. It's a 16 root of unity. So time reversal anomaly is measured mod 16. And we computed this anomaly. We found out that it's n squared minus 1 mod 16. And for no value of, wait, I don't want to say something wrong, but I think, yeah, for no value of even n, this can be 1 mod 16. So this is either 3 mod 16 or minus 1 mod 16. So it's either 3 or minus 1 mod 16, but it can never be 1 mod 16, which is what the Majorana fermion gives. So this also contradicts anomaly. This proposal contradicts anomaly matching with one form symmetry and also with time reversal symmetry.
Can you explain why is it not Z2 by the same argument as for the Z2 symmetry?
Fantastic question. So you can ask why. So this picture that so Slava is asking how to see this mod 16. This is a very difficult question. I mean, the question is very easy, but the answer is very difficult. This picture is in 2 dimensions. I was telling you about some joining and splitting of lines, of ordinary Z2 lines in 2 dimensions. And people have proven that this is a plus-minus thing, which makes a lot of sense. Now, the time reversal symmetry defect is complicated because it reverses the orientation by definition. And secondly, it's not in 1 plus 1, but it's in 2 plus 1. We're now studying a 3-dimensional gauge theory. So people have found that there is some phase, and it's mod 16. It's measured mod 16. And it also has something to do with fermions. So I cannot give you a non-technical answer, but if you want, I'll give you a technical answer of why a root of 16 appears. Are you comfortable with an anomaly inflow argument? Or?
But geometrically, you're saying it follows from the fact that there are some other things in the correlation function.
I cannot explain it geometrically. I know how to prove it using anomaly inflow. I cannot give you a... I don't believe anybody has a reasonably intuitive explanation for this root of 16. It has to do with the eta invariant in 4 dimensions, which is the anomaly inflow. And it's measured in units of 16 because it's generated by RP4. And OK, so in any case, the question in gauge theory was that this proposal contradicted anomaly matching, and we were intrigued to try to fix it. And we found a very exotic fix, but that makes a lot of sense, and it makes many other things suddenly sensible. So the fix was to assume that this model, instead of flowing to just a Gold-Steiner Majorana fermion, it has a topological field theory of the Chern-Simons type. It's a non-abelian bunch of anyons of the Chern-Simons type. Now, this looks ridiculous at first, because topological field theories of the Chern-Simons type typically are not invariant under time reversal symmetry. So if you write the Chern-Simons functional, ADA, it's odd under time reversal symmetry because there is an epsilon tensor. But it turns out that when you quantize Chern-Simons theories, even though classically this is not invariant under time reversal symmetry, when you quantize it, it might become time reversal invariant. And this is very counterintuitive. Usually in physics, you think that if a system has a classical symmetry, it may be violated quantum mechanically. But if a classical system doesn't have a symmetry, it can never be restored quantum mechanically. But this assumes that classical physics is order 1 and quantum corrections are h bar. However, in Chern-Simons theory, there is no classical limit. The classical limit of Chern-Simons theory is an empty, almost empty phase space, essentially. So since Chern-Simons theory doesn't have a classical limit, this may happen. And there is a special set of Chern-Simons theories that nobody has classified yet, but we know of some sequences of special Chern-Simons theories that have a quantum time reversal symmetry. And that's one example of such a thing. You can prove this isomorphism between the topological field theory with these labels and the topological field theories with these labels, which are time reversed by just topological field theory tools. So tacking on such a topological field theory makes sense. It's time reversal invariant.
So this is a level and rank are the same?
No, the level is reversed, as you should, by time reversal symmetry. Oh, I made a typo? No, yeah, it's n over 2, comma n, n over 2, n over 2, comma n. And it's isomorphic as a quantum model. It's isomorphic to its time reverse version. So it makes a lot of sense to tack on this thing. And then a magic happens, as they say, and it fixes the anomaly both mod 16 and the mod n/2. It fixes both of these things simultaneously. So this has a time reversal anomaly, which is either -2 or +2 mod 16, depending on whether n is divisible by 2 or 4. And at the same time, it fixes the one form symmetry anomaly. So one little thing fixes everything immediately.
So it's like inflows in itself, in a sense, because it's in the same dimension, it's not...
This is just a three-dimensional topological field theory. But with this, okay, yeah, so is that clear? So somehow there is a very sexy fix to this problem. There is one thing that you add and it fixes everything. Now, this proposal implies, again, something that people did not expect. It implies that the Wilson lines are deconfined. The adjoint QCD in 4 dimensions, if you've ever thought about it, it's a confined gauge theory. But in 3 dimensions, from these arguments, it must be deconfined because this is a bunch of anyons. So the probe particles are deconfined. And it's somewhat surprising that this is true. So now, how much more time have I got?
Technically 10 minutes and
Okay.
10 minutes for questions.
Okay, so 10 minutes I'll finish, and then there will be 10 minutes in questions. So far I gave you 2 recent applications of the ideas of codimension 2 topological surfaces. There are also some papers that I didn't mention about codimension 3 topological surfaces. But now I want to talk about the non-invertible symmetries. So again, I'll start from an example. So this is now 2 dimensions. This is the last example. Many of you might have thought about this model in the 90s. It was extremely popular in the 90s at some point. So this is just a gauge field coupled to an adjoint fermion in 2 dimensions. It's the same thing that we just discussed in 3D, but now in 2D. What do we need to know about this model? Since there is, again, a one-form symmetry, there is a bunch of local topological operators. So in 2 dimensions, codimension 2 means a local operator. So here, the local topological operators are the generators of this one-form symmetry. And there is a discrete symmetry, which is Z2, just a chiral Z2 for the massless fermion. So when you put m equals to 0, there is a chiral symmetry. Okay, so there is a story about the one-form symmetry again, but that's not what I want to talk about. I want to focus on the non-invertible symmetries. So let me give you some history. In the 90s, this model was very popular, starting from some paper by David Gross, Klebanov, Matitsin, and Smilga. I believe that Matitsin is in Stony Brook, but I'm not sure.
Renaissance technologies.
Okay. So, so what these people argued is that I'm not going to review everything they said, but the bottom line of the paper of this paper of Gross and Klebanov was that the Wilson lines are deconfined, and there is no theta angle in the PSUN gauge theory analog of this model. They also claimed that the Z2 symmetry is spontaneously broken, and so on. So they had a bunch of claims in the 90s. More recently, 2 months ago, more precisely, 2 or 3 months ago, there was a paper by this group of people from North Carolina and Minnesota claiming that this Gross et al. Stuff is wrong. This model is actually confined, except for the Wilson line to the power n/2, which is deconfined. So that's some recent history that I'm quickly reviewing. But we think that both of these things are wrong. So we're working on showing that both of these proposals are in fact incorrect. And the reason is that this model admits a lot of non-invertible topological lines that people have not known. Of course, in the 90s, people haven't known about this possibility, I believe. And more recently, this group did not take into account the constraints from such non-invertible topological lines. So more recently, we've been working on classifying the full set of non-invertible topological lines in this theory, computing their anomalies, computing the fusion rules, and finding what are the constraints on the dynamics that these non-invertible topological lines impose. So mathematically speaking, non-invertible topological lines form a fusion category. A fusion category is a well-defined mathematical object with some axioms, with a pentagon identity, many things that you might be familiar from the Chern-Simon story. But it's not a braided, there is no braiding, unlike in Chern-Simon's theory. So it's a more general object than modular tensor categories that appeared in the context of Verlinde lines. So this is some mathematical object that mathematicians work on classifying, and it has implications for the ground state of gauge theories. So what we are arguing, this is in some work there is some also related work by Costas and Monnier from 10 years ago. So what we're arguing is that these non-invertible topological lines have a lot of interesting consequences for the low energy dynamics of this model. And in particular, what we're finding preliminarily is that this theory actually has a huge amount of ground states, unlike what Gross and Klebanov claimed. We think that there is an exponential amount of ground states, e to the n, which is very bizarre, but this seems to imply, the fusion category seems to imply that. So we think that this model has an exponential amount of ground states, where the Wilson lines are deconfined. And there is a topological field theory that describes this exponential amount of ground states, a two-dimensional topological field theory of this type. This topological field theory is not the same as G mod G that many of you have studied in the 90s. So the bottom line, let me just cut to the bottom line since I'm running out of time. Our proposal for this theory is that there is an exponential amount of vacua in n, so it's e to the n. This means that the Hagedorn temperature goes to 0 at infinite n. The Wilson lines are deconfined, and there is some two-dimensional Frobenius algebra that governs this exponential amount of vacua. This is the summary of the claim. It's surprising that these non-invertible symmetries lead to constraints on dynamics. There are very beautiful examples in this paper of the constraints of non-invertible symmetries on dynamics. This is in the context of RG flows in minimal models. So you can learn a bit about that from that story. And we're also now trying to generalize this whole discussion to non-zero mass, since these non-invertible topological lines only exist at 0 mass. Some of them might survive to non-zero mass. So that's what we're doing now. So let me just conclude with some general comments, which are like homework for Samson. So the general theory of symmetries and anomalies must be extended to include the codimension P defects, which may or may not be invertible. Somebody should understand the axioms that govern the fusion and algebra. It's like a bootstrap problem of these codimension P defects. We don't know what are the correct questions in general dimensions. We know that in 2 dimensions it's governed by what mathematicians call a fusion category. So this theory should be developed. We should be able to classify all the possibilities. We should be able to classify the anomalies as they did with cocycles, group cocycles for ordinary symmetries. And so somebody should lay out the axioms. This is what I explained, that somebody should also classify, generalize the notion of anomalies more clearly for this general setting, the notion of anomaly inflow. What is the notion of anomaly inflow for these Frobenius algebras, for instance? It's not clear. Though there is a very interesting recent paper by Thorngren and Wang about this. Is there a d plus 2-dimensional anomaly polynomial? That's an open question. So here I also made some comments about 2-dimensional adjoint QCD, but the supersymmetric version, we don't yet know about the 1,1 supersymmetric version of the model. We haven't thought about it yet. There are lots of questions about this Hagedorn transition in 2 dimensions, the 0 mass limit, the dualities, and so on. So there are lots of questions that this raises that we don't have answers to yet. So thank you and happy birthday again.
Thank you very much for a beautiful talk. Questions?
So what's this spin n mod SUN topological theory? Could you say in a couple of words?
So as you know about it exponentially more than me. But you know, there is a class of topological filters that people studied in the 90s of the type G mod G, and their fusion rules are basically inherited from a Chern-Simons theory. However, there are many examples of a group. Let's say our example is spin n, a Wess-Zumino-Witten model at level 1, where you gauge SUN at level n. This theory, the central charge of the numerator is the same as the central charge of the denominator. So this is also a topological field theory. But it's not the same as SUN level n mod SUN level n. So you have to develop some formalism to study it. In addition, in our case, there is an additional gauging by some quantum Z2, but that's a minor thing, relatively speaking. So we claim that this vacua and the non-invertible lines, the algebra that they obey is given by this thing. That's the claim. We haven't proven it yet, but we proved it for low values of n. So that's, yeah.
Yes, yes, really.
So this first thing you had with the theta equal pi,
Yeah.
would that also apply to supersymmetric embryos?
Oh yeah, there is, I mean, yeah, since this thing, there is a lot of work on the same thing in supersymmetry. But people haven't studied many questions that you could ask, but for instance, you could ask, is this true in the cyber kind of theories with some softly deformed? And Popitz wrote a paper about it. There is a paper of Popitz, there is a paper of somebody else whose name I forgot, unfortunately. And they seem to find a similar picture with a spontaneous breaking of time reversal symmetry and a compelling argument for the existence of anyons on the boundary.
So you end up with a symmetry breaking picture in that case.
I don't know if this is always what they found, but I remember one example where they found exactly this picture in some softly deformed supersymmetric model. I don't know if this is always what you find. You might also find this kind of thing. I don't know the general answer.
I have a couple of questions. First of all, is your exponent of n better said 2 to power n?
Yeah, it's 2 to the power n. I'm sorry.
And also, I remember Anton Kapustin told me many years ago that the whole thing should be this stratified manifolds and get different chemical series.
Say again, I don't know this.
No, this general point of view of this high extended topological, not topological field theory, you put kind of stratification on your space and you get different observables, whatever, on different strata. And mathematicians, I think now around Castello, they have.
Right. Yeah, there is some framework where there are objects of codimension 1, 2, 3, and they have some rules of how they talk to each other.
In your situation, this all defect kind of series topological and defects, not on a.
Right, but my understanding is that they don't actually know all the axioms for the junctions and fusions of these defects. That's my understanding. In 2 dimensions, people have worked out the axioms and they worked out the pentagon identities and they proved the rigidity theorem. Okay, now we'll prove this rigidity theorem, so we know that there is a discrete set of fusion categories, and that's why there is anomaly matching, because it's a discrete set. But I don't think anybody has done analogous work in higher dimensions, but I might well be wrong. Yeah, I might well be wrong.
Yes.
So about your second example.
Okay.
I'm not sure my question makes sense, but so since you are in 3D and you have this codimension 2 operators which are lines, which can wrap around lines, what happens with the operation if there are 2 symmetry operators which wrap around a line on which they act and also simultaneously around each other?
So your picture is that you have 2 lines that are knotted?
Yeah, and also they act on some line operator.
And also another line that goes in between.
On which they act. So this seems to define a new type of product, because you said that this algebra is commutative.
No, this would reduce to something that we know. So you're asking about sorry, let me just draw it correctly. You're asking about this, and then another line that just goes through.
No, but it should go through. It should go through both of them.
Oh, you want to go through both
So
of
that
them?
they both act on that line.
You have linked.
Yeah, this is already linked, and now you want.
But they link.
Oh, you want this to go through this one? Okay, now I understand.
Yeah, something like that. Yeah.
Okay.
So because you said that this algebra of codimension 2 operators is abelian, but this seems to define a different sort of product, which is not clear to me if it's abelian or not.
No, so we have a distinguished set of n lines which form Zn, which are the generators of the one-form symmetry. Now this line,
On which they act.
this could be a different line on which they act.
I agree.
Yes.
In my example, it's a different line.
It's,
What is this product between the 2 circles?
but you see here there is no action, so you have to first fuse this line with this and then act. So this is a symmetry line, right?
Yeah.
So first, how would you reduce this? You would first fuse this and that. So you have to fuse the line on which they act with one of the topological lines. Let's call this W. You fuse them, you get some new line, which is not topological in general. And then this guy, which we can call W prime, would act on it.
Okay, I'll ask you later. Yeah, I'll ask you later. Thank you.
Well, if these are all symmetry lines, so in the case of 3 dimensions, since the lines and the symmetry lines and the symmetry generators are all lines, so the lines can act on themselves. So if these are all symmetry lines, then I can reduce it by fusion and by a sequence of fusion and contraction moves. It's an abelian thing. But yeah, I mean, definitely, this is what you should think about when you think about the general framework of all the possible ways in which you could draw such pictures. Yeah.
Is there an example of a non-invertible operator that can be understood down to earth terms?
The question is if there is an example of a non-invertible operator that can be understood by down-to-earth terms. That's what you're asking?
Yes.
Yeah, the simplest example is the simplest example is in the tricritical Ising model. Well, also you could also say the simplest example is probably in the Ising model itself. So in the Ising model, there is at the self-dual point, there is the duality symmetry. And this duality symmetry, you can think about it as being implemented by some kind of codimension 1 defect. And this codimension 1 defect is not invertible. So when you fuse it with itself, you get 1 plus epsilon rather than 1. So the best place to look for the simplest possible examples, these are in minimal models. And there is a huge amount of examples in minimal models of non-invertible lines in this paper that I briefly quoted by Chang, Lin, Shao, Wang, and Yin. They looked at tricritical, the Ising model, and some rational CFTs, where they have a huge... I mean, another very clear set of such examples are Verlinde lines, of course. The Verlinde lines are, in fact, like the first set of such things that you've encountered, maybe. The Verlinde lines are more special than the most general case, but this is a bunch of non-invertible lines in two-dimensional rational conformal field theories.
But there they're defined axiomatically. Down to earth means like you take a lattice model and you see...
Oh, you meant something down to earth like in that sense. Okay, so then definitely you should look at this paper of Chang, Lin, Shao, Wang, Yin. They have lots of references to condensed matter constructions where you can see these things on the lattice explicitly.
Since he gave me homework, can I ask questions?
Yeah, of course.
So we're in the old story where ABG and all other anomalies.
ABJ is not an anomaly. ABJ is a confusion.
So there is an action, something is anomalous. It's some group action or something. It's given from the beginning. They tell you that there is some group which acts somewhere, and then happens that it is anomalous. Here you not tell us what was replacing the notion of group.
Right, so for the case, okay, I'm not telling you because I don't understand the answer. But people claim that they know the answer. So for this case, in some special cases, people know the answer. So in this case, I know the answer. Here, what replaces the group, the gauge fields are two-form gauge fields. So instead of writing anomaly inflow for one-form gauge fields, like A wedge dA, you write B wedge dB. So here, what replaces the notion of anomaly inflow is just two-form gauge field anomaly inflow. In this case, people claim to know the answer, but I don't understand it. It's in...
That's why the other one is abelian, you say always?
Yeah, the other one is abelian because two-form gauge fields are always abelian. But the non-invertible lines are genuinely non-abelian. And there is the mathematical meaning of the notion of anomaly inflow is explained in this paper that I don't understand.
Is he a mathematician or physicist?
He's a mathematician / physicist. He's a physicist. Yeah, it's something to do with well, I don't even want to say because I don't know what this means. But it's some kind of...
But there is a proposal.
Yes, there is a proposal for what it might mean. Yeah. In 2 dimensions only. It's only in 2 dimensions that there is a proposal.
Yeah, I think we have to bring this question session to a close because we have another talk immediately after Zohar's talk now. So thank you again.
Thanks.